Today we are working with homework problems from Chapter 4, and we are also doing a review for our midterm exam, which will be held next week. Now, I had given you 4 problems as review problems for the midterm. These are posted to our Moodle page, and I just had a question from the class about Chapter 3 property tables. And the example I gave was problem 320. So let's go ahead and work through that a little bit. There's a very specific question from your classmate here, but I'll just go ahead and work it through and hopefully answer any questions that you have. And that way, so it'll take a little bit longer, but we'll be able to answer all of the questions that you may have. All right, so on problem 320, we have a table for water, first of all. Oh, here I am with this bad pen again, sorry. So my substance is water. And do you have, in problem 320, there are 1, 2, 3, 4 problems. Did you have one of those that you wanted to start with?
The third one.
The third one. So we have a temperature of 190 degrees centigrade and a pressure of 2,500, right? Okay, so we have temperature is 190 degrees Celsius, and the pressure is 2,500, and we're in units of kPa. All right, so I have to flip this over here to my document can. There we go. All right, so these are the parameters: water, temperature 190, pressure 2,500 kPa. So the first thing that we need to do is to go to our property tables, and you will have access to these while you're taking the midterm. You'll either have them, I'll either give you pages, probably not, but that would be in a pinch, I would do that. Or you'll be able to access your property tables from the Moodle page, or you'll be able to open your textbook if you're Zooming with me or if you are taking it face to face. So I always think with problems like this, I always think about the two-phase region or the saturated liquid vapor line as kind of being in the middle. So if I look at the saturated water temperature-based table and I go down to 190 degrees, what I see is that the pressure to keep it in the two-phase envelope is 1,255.2 kPa. Okay, so at 190 degrees, Psat is 190. Thank you so very much. 1,255 kPa. All right. So what I see then is that my pressure is higher than this. Okay, I'm going to flip this back over. The pressure that I have existing in my problem is higher. So if I think about that two-phase envelope as being in the middle, and this being a temperature and pressure corresponding to my saturation values, a higher pressure is going to boot me down here into the compressed liquid range, isn't it? Okay. If the pressure was lower, it would put me over here in superheated gas or superheated vapor. And if both were higher, it would be supercritical. But we were really not dealing too much with supercritical fluids at this particular point. All right, so now what about compressed liquid? You may or may not have good tables for that, but we're going to go down and take a look, see what we have, and then we're going to make some assumptions, because that's what we do as engineers. We try to make good assumptions. These are superheated, so clearly that's on the other side. That's on the left-hand side of the two-phase envelope. And this is saturated ice water vapor. This is the sublimation curve, which is an interesting place. But basically, these are the temperature and pressure conditions at which water will not liquefy, but it will go directly from a solid to a vapor. And they tend to be, as you see, slightly below freezing with extremely low pressures. So we're definitely not here. This area of behavior doesn't even show up on the chart that we generally draw. It's kind of sideways to it, but you can draw it if you plot P versus V, it sort of looks like this, where you have this area of sublimation. I haven't labeled the axes because I was just doing this. And then you have a triple point where all three phases coexist, and water just has a single value of temperature and pressure where all three phases will coexist. All right, so what this means is we don't really have any good tables, at least here, for, well, here we have some compressed liquid water tables. So let's see what we have. Oops, you can't even see that. There we go. We do have some compressed liquid water tables. So here's superheated vapor. And afterward, we have compressed liquid water. Now, our pressure is 2,500 kPa. This table is listed in MPa. So that means we would be at 2.5 MPa. So that means that we're in between here and here, isn't it? So in other words, we're in between. Let me do this. Come back over here to the smallest value we have is 5 MPa, which is 5,000 kPa. That's the smallest tabulated value that we have. Now, what we know is that if we were right here, we would have a pressure of 1255, and somewhere down here, we have a data point here, and we have a data point here. Somewhere over here, we have a pressure of 5,000, and our pressure is somewhere in the middle, 2,500. Okay? The other thing that we need to think about is, because we don't have that exact data point, thermodynamic properties of water, but of most substances, are much stronger functions of temperature than they are of pressure. Okay? So that's just something that we would think about here. It's not going to make a difference in our calculations. But if we find the data here where we have a temperature of 5,000 and we find out that our temperature, let's see, my temperature is 190. We have a point right in between 180 and 190 for those two things. Okay? But I'm just going to write that down. And then, of course, here we have that exact point, which is in the saturated region, which is 190. All right. So if we look at that problem and continue our thoughts, we have 190. We want to have the U value, and we want to have the phase description. Okay. Well, the phase description is compressed liquid. All right. But what is U? Well, how about if we found U here and we found U here, and then we did a little interpolation between them? Okay, what you're going to find is there's not going to be a lot of variation, is what I'm telling you. But let's go back to the compressed liquid table.
So it'll just be halfway between 180 and 190?
Yes, that is correct. So if you look here on this table, for my data point, my U value for 180 degrees is 759, and at 200 degrees, it's 847 degrees. And I apologize, we don't have 190, we only have 200. Okay, so my answer to that would be halfway in between those two. We would add the two values, 759.47 and 847.92. Take the sum of those two things. I'll put it back on the document cam. Divide it by 2 just to get the middle point or the arithmetic mean of those two values. So I get 803.695, and that is in kilojoules per kilogram. Okay?
So that's what it is.
That's what it is right here. Now let's find out what it is right here. Okay? So we're going to go back to the compressed liquid, or to the saturated liquid tables. And we want to go to that point where we are at a pressure. Well, now it's going to be a stronger function of temperature. So we want to go to 190 degrees. Okay? So if we take a look at our saturation at 190 degrees, I'm in the pressure table still. I'm going to come up here. Here we go. Okay, 190. You can see that my U value there is going to be U sub F because I'm right on the edge of the curve, right? And so it's 806. And it's 806 even. And once again, it's in kilojoules per kilogram. All right, now let's take a look at our work. We have a point here where the U value is 803.695, a U value here, which is 806. What can you say about the U value of a point somewhere in between the two? Exactly. It's somewhere in the middle. It's somewhere in between. And we could interpolate. If I'm going to go ahead and do this, I wouldn't ask you necessarily to do this, but we're on the same temperature line. We're at 190 in both cases. So if we set up our pressure at one point is 5,000, the point we want is 2,500, and the pressure here is 1255. Okay? Then the U value for my 5,000 is 803.695. Right here is we don't know, and right here is 806. In units of, this is kPa, and this is kilojoules per kilogram. Okay? All right. So we can interpolate, but I want to tell you, if you got to this point and you said, I'm just going to use 805, that would be fine with me. But I want to show you the process of interpolating. So what we do is we find the ratio between this and this compared to this. So we take 1255 minus 2500 and put that over 1255 minus 5,000. So that's the percent that this number is from here compared to this number from here, the whole amount. Then I set it equal to 806 minus whatever our question mark value is, the U value that we want, over 806 minus 803.695. This process is called interpolation. Okay? So if we find this ratio, 1255 minus 2500 divided by the quantity 1255 minus 5,000, we find that that ratio is 0.3324. That's going to equal 806 minus question mark over this number, which is 2 point something, negative 2 point blah, blah, blah. All right? So I want to take, if you think about it, you cross multiply, and I would get 806 minus that question mark is equal to 0.3324 times this number, 806 minus that. So let me just go ahead and do that. I'm going to times that by parentheses 806 minus 803.695 parentheses equals. So I get that number is equal to 0.76628. And if I bring the question mark over to this side, to the right-hand side, 806 minus 0.76628 is going to be the value that I want here. So I just, that's 806.
Where did you get 806 from?
Right here. Yeah. It's just in the table at 195 on the, let me put it over here for you, Isaac. Oh, sorry. So this is our saturated water table, 190 degrees, U at 0% steam quality. So in other words, that point, that 806, corresponds to this point on the edge of the two-phase envelope. Okay. So anyway, that number, my question mark, turns out to be 805.23, and that's in kilojoules per kilogram. So equals 805 kilojoules per kilogram. Okay.
So on the midterm, you want us to interpolate?
No, I don't. I wanted to show you how to do it. If you're really and a lot of times you'll notice that you're off the edge of the curve, you're off the edge, but you're making some assumptions in there, so it's not really 100% accurate to do a linear interpolation off the side of the curve like that. However, it's the best number. Yes. And that's why I said just pick 805, It's just like, it's kind of, or 804 and a half, or, whatever. Just tell me what you pick, And as long as it's somewhere in that range, I'm good. All right, yep.
And then the last one has like a pressure of 4,000, and it gives you U.
Yeah.
You have to find out the temp.
And the phase description, huh?
Yeah.
Okay. So on the last one, on number 20, we have water once again. We have a pressure of 4,000 kPa and a U value of 3040 kilojoules per kilogram, and we want to find the phase description, and we want to find the temperature. Okay, so the first thing I would do is go to that saturated, in other words, my two-phase envelope, the saturated water. Now we can't use the temperature table, but we can go to the pressure table. And once again, this is going to be in the middle. So we find our pressure, 4,000 kPa, right here. And what do we see about the U value? Well, if it was all liquid, in other words, you need to see this, I apologize. Let's go again. Saturated water, pressure table, pressure of 4,000 kPa. Come over here to the values that you're given, the U values. If we were on the left edge of the two-phase envelope, our U value would be 1,082. If we were on the right edge, it would be 2,600. That means that we have too much energy for it to be in the two-phase envelope, right? So we are off to the right. The phase is superheated vapor. Okay? Now, we go down then to find out what our what our temperature is here, and we can look at superheated water. Our pressure is 4,000 kPa, which is 0.4 MPa. So each of these tables is organized by pressure. Okay? And if you look at that, let's look at the values of U. Our value of U is 3040. If you go here, you'll see that we're in between the temperatures of 400 and 500. Okay? So at a temperature of, we'll interpolate again. At a temperature of 400 degrees centigrade, then we have an unknown temperature, and then we have a temperature of 500 degrees centigrade. At 400, our U value is 2964.9, and our U value is 3040. I'll put this on the screen in just a minute. And if we were at 500, it would have a U value of 3129.8. Okay? Come back here to the document, Ken. So here's our interpolation. Okay? This time to find our question mark, we can take this compared to this, 3129.8 minus 3040 over 3129.8 minus 2964.9 equals 500 minus our temperature, we don't know what it is, over 500 minus 400. Okay, so finishing that off, finding this ratio, 3129.8 minus 3040. Divide that number by the quantity, 3129.8 minus 2964.9. So that ratio is 0.544. We're almost halfway in between. 0.54457. Now, when we cross multiply, 500 minus 400 is just 100, right? So that's going to equal 500 minus our unknown value. So we take that ratio, multiply it by 100, and that's 54.46 equals 500 minus question mark. So that means that our question mark value, if I bring that over as a positive, is 500 minus 54.46. And so my value is 445.54 degrees centigrade, Celsius. So my temperature then is my phase superheated, my temperature 445 degrees Celsius, or 446. We really can't cut it up any finer than that. Our temperatures are in whole degrees, so it makes sense to report our temperature as a whole degree. And whether you call it 445 or 446, we're doing this interpolation that's making this big old broad assumption that it's perfectly linear, so I'm good with either of those numbers.
Does it matter if you say superheated vapor or superheated water?
Either's great. Yep, superheated is the key. You bet. So you guys ask good questions. Okay. What else do you want to know?
I had a question on the first. I think it's 4-4.
4-4? 4-4 says calculate the total work in BTU for the process from 1 to 3. Okay. Let's take a look at this. This is a good problem, and I'm going to show you how to work it out. I don't think I will work it out directly. Okay. If you think about this, this is a pressure versus volume curve, right? Well, what do we know about work? We know it's this integral. That work is equal to the integral of P dV. One literal interpretation of an integral is the area under the curve of the P versus V graph. Okay, so that's a thingy from calculus. So if you find the area, and what area is it going to be? Well, this is going to kind of include that, right? So, because you're actually, if you think about it, you're compressing from here to here. So it would be, right, or another way you can do it is just literally do the graph, which would be this graph, that rectangle, and this triangle right here. So in other words, yep. How's that?
So I had the, is it, like for the first one, would it be like 15 psi a times 1 foot cubic foot, or would it be 1
Well, it's times, right? Because look at that. Yeah. Now the only thing that you need to make sure you do is PSIA is pounds per square inch. And so you're going to have pounds per square inch times feet cubed. You need to convert it either into inch pounds or pound feet. Yep. But yeah, so it's times. So yeah, and it's just like the most literal interpretation of that integral is what it amounts to. And that comes in handy a lot because a lot of times you can get lab data that looks like this. And then if you don't really know what the relationship looks like, mathematically, you can still just do the area. So, all right. Oh, yeah, and just remember, and the limits, because it's PdV, the limits are going to be from V2 to V1, or from V1 to V2. So just, make sure that your delta V is the change in the volume over the whole thing. So, yeah. Yeah. And what else do you want to know? All right. Well, I think you guys are going to be fine. Like I said, when we have our midterm next week, if you're both taking it on Tuesday, I'll be with you. You know, I might put you in a conference room if there's only a couple, but if there are a lot of people show up, we'll just be in here. Otherwise, we'll be in the conference room, and I'll just be available to you to answer questions. You know, not like how do you do the problem, but you know, like what are you getting at, kind of thing. So, I need this piece of data. How can I, you know, I can help you with things like that. So, all right.
I have my textbook on a PDF on my iPad.
Absolutely. Yeah, you can use it. Yep. Just don't go off into the internet,
Yeah.
right? Don't phone a friend, in other words. But yes, if you are, if that, because I do exactly the same thing. I mean, I keep all my textbooks. I mean, like in this class, I bring it in here, but like when I'm working on things, I always have it in my office, and I have the document I'm working on one screen and my textbook on the other. So I'm completely lost without that. So
Yeah,
it's.
I have a copy of my textbook. That one of them has the tables, and the other one has the problems. And
Okay,
stuff.
yeah, that's great, isn't it? It's helpful. It's very helpful. So I love having a split screen or double screens. I mean, it's just like, it makes so much difference. So it's good stuff. All right, well, that's it for today. If you have any questions, don't hesitate to ask. I will be on campus. I may leave a little early tomorrow, but I'll be on campus tomorrow if you need me. I'll be on campus all day Monday and Tuesday. I'll be here Wednesday till about noon of next week. So then I'm going to Laramie for a research summit, which should be really interesting. But I'll be around up through everything about your testing. So if you're not able to take it on Tuesday, just make sure to make an appointment with me. But otherwise, we'll see you Tuesday for the exam. So.
There's no class next Thursday.
Yeah, no class next Thursday. Good point. So, yep. Well, some people will still be taking their midterm. So by taking it on Tuesday, you're actually buying yourself another few days. So, all right. Thanks, guys.